Hello all. So in the last session we were discussing about sequence to sequence model, and we've already discussed about one model, which is machine translation, and how to build a machine translator. So today in this session I would like to discuss about how sequence to sequence model work. That is the functionality of sequence to sequence model. So in the previous session we have seen the sequence to sequence model consists of two main subcomponents, that is the encoder and a decoder. Basically, the encoder will take the sequence of some inputs and then it converts that into some internal representation like this. Okay. Now the decoder block, on the other hand, will try to generate a sequence of some units with respect to the sentence representation from the encoder block, right? So let us see the individual functionality of encoder and decoder. Okay. Now the encoder of a sequence to sequence model is basically much like sequential labeling models, and its main functionality is to take the input sentence as input and convert that into some fixed length vector representation. Okay. So when I talk about encoder model, we use simple LSTM or RNN model as shown in the figure below. Okay. Unlike the basic sequential modeling where we take only one layer of RNN cells, we can also have multi-layer RNN as encoder. Okay. As you can see in the figure below, we are using multi-layers. I'm using here 2 layers for the encoder block. Okay. So even if you take one layer or 2 layer, the final hidden state of the RNN is then passed to the decoder to generate the target sequence as we have discussed. Okay. Now, similar to multi-layer, we can also use bidirectional multi-layer RNN as an encoder block. Okay. Whereas here in this case, the final sentence representation would be the concatenation of the output of the forward layer and the backward layers as shown in the figure below. Okay. So that is not just simple RNN, but also you can use multi-layer RNN or bidirectional RNN for the encoder block. Okay. Now when I talk about encoder block, we can use a simple RNN or LSTM. If suppose we use LSTM cell, that produces two types of output, the cell state and the hidden state. Okay. So when you're using LSTM for encoding a sequence, we usually just use the final hidden state while discarding the cell state here. Please make a note of this point. Okay. So just think that cell state is something temporary loop variable which is used for computing the final outcome that is present in the hidden state, as you can see here in the figure below. The output of the final hidden state is only used for calculating the sentence representation. Okay. Now when I talk about decoder, the decoder of the sequence to sequence model is much similar to the language model. In fact, there is one difference. Okay. So the difference is that the decoder takes an input from the encoder here in this case, whereas for the language models that we have discussed earlier, we have no input given to that. Without any input or without any precondition, we develop the language models which we have seen earlier. So therefore, we call them as unconditional language models. Okay. Whereas for the decoder model, where we use the architecture similar to language model, but the input is coming from the encoder model, we call them as conditional language models. Okay. So sequence to sequence decoder is one type of conditional language model. Okay, as you can see, this is a decoder model of a sequence to sequence model. Here we are taking input from the sentence representation. We are declaring some input here. So we call this as conditional based language models. Okay. Now, just as with language models, sequence to sequence decoders also generate text from left to right. Okay. Now, the decoder here can also use multi-layer, but not bidirectional. Okay. Now, we call this condition of operating on the past sequence as autoregressive models. Okay. Now let us see what are these autoregressive models and what are non-autoregressive models. Okay. If generating text from left to right is too limiting, okay, we have a good point, because humans also do not need always that we write language linearly, right? Because we add words, we delete the words, we make some changes in the phrases afterwards. Okay. So when we are trying to generate the text in a linear fashion, it is not very efficient. The later half of the sentence need to wait until the first half is completed if you are doing any modifications, right? Which is very difficult to parallelize the generation process. So I have to put in a lot of effort into developing non-autoregressive machine translation models that do not generate the target sequence in a linear. Okay, so we have this non-autoregressive models where we can improve the quality. Okay, now, however, the decoder behaves in a bit different between training and the prediction. Okay, now let us talk about the training phase. Okay, we know exactly how the source sentence should be translated into the target sentence, right? Okay, so we know how exactly the decoder should produce word by word. Because of this, the decoders are trained in a way similar to how sequential labeling models are trained. Okay, so basically what we do is, firstly, the decoder is fed with the sentence representation which is coming from the encoder. Okay, along with this sentence representation, a special token also is generated which indicates the start of a sentence. Okay, so once the decoder receives this, the first RNN cell processes these two inputs and produces some hidden state. As I told you earlier, forget about the cell state. Okay, it produces the first hidden state, and the hidden state vector is fixed to a linear layer that either shrinks or expands this vector to match the size of the vocabulary. Okay, now this resulting vector then goes through the activation function, that is probably we will be using softmax, which converts it to a probability distribution. Okay, now this distribution dictates how likely the word in the vocabulary is to come next. That is the main duty of the language model. Okay, so here the sentence representation will be done along with the word token, special token, and each RNN will use the update state. It will discard the cell state and process the only hidden state, and this will be processed through a linear layer through an activation function which will have distribution over vocabulary and generate the output. Okay, now when I talk about, when you observe this figure particularly, okay, we have so many things that we have to analyze. Okay, now this is where the training actually happens. Okay, now if I consider the input is Maria no daba, okay, if I continue Maria no daba or something else to that, we would like the decoder to produce its English equivalent, saying Mary did not slap, or whatever it is. Okay, for example, let me take only three words. Okay, Maria no daba, which means the English conversion is Maria did not. Okay, now this means that we would like to maximize the probability that the first RNN cell here generates Mary given the input sentence. Okay, now we call this as multi-class classification problem because we have seen about this so many times. Okay, now we use word embeddings, we use sentence representation, sentence classification, all that stuff. Here we can use this cross entropy loss to measure how far apart the desired outcome is actually from the original output of the given network. Okay, if the probability of the word Mary is large, okay, then the desired outcome is good. Okay, now the network here will incur the small loss. Okay, on the other hand, if the probability of Mary is small, okay, then the network will incur the huge loss. Okay, which encourages the optimization algorithm to change the parameters by large amount. Okay, now after we are done with this Mary conversion, we move on to the next cell. Okay, after we move on to the next cell will receive the hidden state computed by the first cell and the word Mary, regardless of what the next cell has to be generated. Okay, so instead of feeding the first token generated by the previous cell, as we did when generating using text using a language model, we constrain the input of the decoder so that it will not go astray. Okay, now here this particular second cell produces the hidden state based on these two inputs. Which two inputs? The word Mary and the next word that we are supposed to predict. Okay, now based on this, we will compute the cost. Based on this, we will generate the probability distribution for the second word as well. After this, we again compute the cross entropy loss by comparing the distribution against the desired output did and move on to the next cell. We keep on doing this until we reach the final token. Here I've taken 3 words for showing you an example. You can continue this till you reach to the final word. Okay. Now, after we reach the final word, the total loss for the sentence, that is the average of all losses. If you have take 3 words, the average of 3 loss would be computed in a way we adjust the model parameters of the decoder so that it can generate the desired output the next time around. Okay. Mainly important, please note that the parameters of the encoder are also adjusted in this process because the loss propagate all the way back to the encoder, not just decoder, but also till the encoder through the sentence representation. If the sentence representation produced by the encoder is not good, then the decoder won't be able to produce high quality target sentences no matter how hard it tries. Okay. So now let's look about 2 types of grading methodologies. One is called as greedy decoding. Okay. Now let's see how does the decoder behaves at the prediction stage. Okay. When we are giving a source sentence as input, we doesn't know what correct translation should be. That is the reason at this stage, a decoder will behave a lot like language models. It is fed with the sentence representation from the encoder along with the special token. Now, the first RNN cell process these 2 inputs and produce the hidden state, which is then fed to the linear layer and the softmax to produce a probability distribution as we have seen here, right? Now, this is how the prediction is done using a sequence to sequence layer, right? Now, here comes the key part. Unlike the training phase that we have seen here, we do not know the correct word to come next because we'll have multiple options. You can choose any random word that has reasonably high probability. Okay. If you're lucky, we may get word Mary only, but sometimes we may get other words also. So the empty system here produces the word that was just picked and then feeds it to the next RNN cell. Okay. Now we are all good here. Okay. Now, after we are done with this, when we evaluate our empty system, because it is doing everything it can produce, we are not sure about the best possible translation, right? So here comes the key part. Unlike the training phase, we continuously repeat the process. Okay. So first of all, the goal of the empty decoding is to maximize the probability of the target sentence as a whole, but not just as individual words. This is exactly what we have trained the network to do to produce the good probability for the correct sentences. But sometimes the words that are picked at each step described earlier to maximize the probability may not function properly. Okay. Now this type of myopic is locally optimal algorithm. In computer science we call this as greedy, and hence this decoding algorithm is called as greedy search. Okay. However, just because you're maximizing the probability of individual words at each step doesn't mean you're maximizing the probability of the whole sentence. Got it? So these greedy algorithms basically in general are not guaranteed to produce globally optimization solution, and using this greedy algorithm can leave us stuck with suboptimal translations, which leads to very poor accuracy. This is not very intuitive to understand. So let me use a simple sentence to illustrate this. Okay. Now when you're picking up words at each time step, you have to choose multiple words to pick from. Okay. Now this is one example that I would like to describe. Okay. Now, as you can see in this particular figure, which is represented as a tree structure. Okay. Now, this diagram shows how the word you pick at one time step. For example, when I choose did, okay, branches, this particular word did branches out to another set of possible words. Okay. As you can see, you and not, right, to pick up for the next time step. Okay. Now, this greedy decoder, the diagram that you have taken here, this greedy decoder that we have seen earlier will have 2 choices. It generates did at time steps 2 and that did will generate U and not. Now U has a score of 5 and not has a score of 3 because all it does is pick the one with the highest score. We will pick U. Mary did you, because it has the highest score, and then move on. Then after this it will face another branch with time step 3 generating the score of 1 or generating no with the score of 2, and again it moves on. Okay, now it will pick the largest score, that is no. Okay, and then you will end up with the translation Mary did you know. Mary did with 5 score, you with 2 score, and no, that is 1 plus 5 plus 2, that is equal to 8. This is not a bad result. At least it is not as bad as the first part where we get Mary did you do with the score of 7. By picking up the maximum score at each branch, you're making sure that your final result is the least decent. Okay. However, what if you have picked not? If suppose I picked not, okay, it here at time step 3, what if we have picked not? That is a question here. Okay, at first it is smaller, then you would be getting another path. When you move on to this step, we have only one thing. The score here is 9. Okay, so in this way we would process the greedy search algorithm. Okay, each transition from word to word is labeled with a score which corresponds to how large the probability of choosing the translation is. So the main goal here is to maximize the total sum of the scores that when you traverse one path from time step to 1 and 4. So here I've taken 4 time steps. So we traverse one path from time step 1 to 4. Mathematically, the probabilities are real numbers between 0 to 1 and you should multiply each probability to get the total. So when you go for Mary did you do, the total score is 1 plus 5 plus 2 plus 1, that is equal to 7. Okay, so this is one idea. Okay, now if you have multiple words, okay, so if you have multiple words, then you'll have a problem, right? So for that reason we go for beam search decoding. Okay, the main idea of beam search decoding is instead of committing to one path, it pursues multiple path called hypothesis at the same time. Okay, as you can see here in the figure, beam search decoding algorithm will have multiple paths promising good results. Okay, let us see this in action using the figure below. As you can see, this is slightly modified version of this because each word will have multiple paths. Okay, now the key idea of beam search decoding is to use a beam which you can think of some sort of buffer that can retain multiple hypotheses at the same time. Multiple hypotheses, as you can see here in the bottom figure, it will have multiple hypotheses at the same time. The size of the beam, that is the number of hypotheses it can retain, is similar to the beam width. Now let us use beam of size 2. Okay, so here we are using beam of size 2 and let us see what happens. Okay, now when you take this beam of size 2, okay, for example, when you move on to did, okay, when you move on to did here, okay, Mary did, okay, from first word to second word in the timestamp here, it will make new hypothesis consisting of Mary did with a score of 1, okay, which will have 3 different sentences being generated. Okay, so what are the 3 different sentences? Mary did you, Mary did not, Mary did. Okay, so these are the 3 different possibilities. Okay, now with this, if you have multiple words to choose from a particular time step, a hypothesis can span multiple child hypothesis. Okay, so here in time step 2, we have 3 different choices. You, not, in. We generate 3 new child hypotheses with different scores, 6, 4 and 3. Okay, now here's the key part of beam search decoding. Because there's no much room in the beam, the hypotheses are not good fall off of the beam after sorting them by their scores, because the beam can hold up to two hypotheses in this example, accepting anything except the top two gets kicked out of the beam. Okay. Now, after you see this at time step 3, each remaining hypothesis can span up to two different child hypotheses. And the first one, Mary did you with the score of 6, will generate Mary did you know with 8, Mary with, okay. Whereas the second one, Mary did not with score 4, turns into Mary did not slap with score 9. These three hypotheses are sorted by their choices, and the best two will be returned as a result of the beam search decoding. Okay. Now, an algorithm will be able to find the path that maximizes the total sum of scores by considering multiple hypotheses at the same time. This is how the decoder works. Thank you so much.